So let's solve for another problem, but this time we would be dealing with a design problem. So in this problem, we are to design an SMAW fillet weld to resist a full capacity load of the 10 by 150 member as shown. So this would be your 10 by 150 mm. So we are to use a 572 grade 50 steel for the members and E70 electrodes for our welds. And we are to use ASD and LRFD for our designs. When we are to design fillet welds given this setup right here, what we are actually solving are the value of our length of the weld and the nominal size of our weld. So from those two, we can actually solve for this one right here right away. So for our A, or the nominal size of our weld, for the minimum nominal size of our fillet weld, we would be referring to this table right here, which I have shown to you in the previous video. So this thickness right here, once again, is dependent upon the thickness of the thinner plate here. And as you can see here, this big plate right here is to be 12 mm, and this plate right here has a thickness of 10 mm. And from those two, we can now conclude that this plate right here is to be thinner with a thickness of 10 mm. So from that thickness of 10 mm, we would now categorize it here, and according to this table right here, 10 mm falls under this category. So 10 mm is greater than 6 mm, but it is less than 13 mm. So from that, the minimum size of our fillet weld is now equal to 5 mm. So 5 mm. So if that is to be the minimum, so what would be our maximum? So from this statement right here, once again, since our plate right here has a thickness of 10 mm, meaning it is greater than 6 mm, it may not be larger than the material thickness less than 1.6 mm. So once again, our A max is equal to 10 mm, which is the thickness of our plate, minus 1.6 mm. And 10 minus 1.6, that is equal to 8.4 mm. So meaning our A max right now is to be 8.4 mm. So if this is to be the minimum and this is to be the maximum, what A would we choose, or what size would we choose? So it would depend upon the designer, whichever of these two he or she would choose. But take note, guys, that if you would be choosing this, you would arrive at a much larger LW, so higher LW. And if you would be choosing this, you would be arriving at a shorter LW. Or you could choose in between, so let's say 6 mm, 7 mm. So it would be up to you as long as it would be in this range right here. Okay, so how can we solve for LW? Since it is said here in this problem that it is to resist the full capacity load of the 10 by 150 member shown, we would be checking the capacity of this section right here. And since this is to be a tension member, we are to solve for cross-sectional yielding and tensile rupture stress. So there. And for our cross-sectional yielding, so let's solve for it first. For our PN, in terms of cross-sectional yielding, this is to be AG times FY. And our AG and FY respectively are, so when we are to use this, 10 by 150, so 10 by 150 times Fy of 345. So 345 megapascals. So our Pn right now is equal to 517,500. So 517,500 newtons. And if we are to convert this into kilonewtons, this is equal to 517.5 kilonewtons. So that is for cross-sectional yielding. And how about for tensile rupture stress? Pn is equal to Fu times AE, where Fu is to be our rupture stress and our AE is to be our effective area. And our effective area is equal to shear lug factor times the net area. And since we don't have any holes in here, our net area is also equal to our AG. But what about for our shear lug factor U? So for our shear lag factor, we would be referring to this table right here once again, which is very familiar to you already. And as you can see here, our welds are in this setup right here, which is longitudinal welds only. So we don't have any transverse welds. So from that, we would be basing our shear lag factor in this case right here, which is case number 4. So plates where the tension load is transmitted by longitudinal welds only. So we can either use 1.0, 0.87, and 0.75. So what we would be comparing is the length of the weld L and the width of your plate or your section. But the thing is, we don't know what the value of RL is. So as you know, we are actually solving for this. So if we are to get these limits right here, so 2W, 1.5W, and W, so what is to be our W? So our W right here is to be 150 mm, since this is to be 150. So going back here, this is to be 300 mm. This is to be 150 mm. And as for this, I think this is to be 225 mm. If I am not mistaken, let's just check. So 150 times 1.5. So yes, that is to be 225 mm. So what you would be doing right now is that you would be guessing on which L would fall. If it would fall here, if it is greater than 300, you would choose shear lag factor 1. If you think that the one that you would be solving later would range from 225 to 300, you would be using 0.87. But if you think that your weld would fall on this category right here, which is greater than 150 but less than 225, you would be using 0.75. So it is a matter of guessing right now. But take note, guys, that if your guess is incorrect, you will just be resolving it. So there, but I just think that the LW that I would solve would fall in this category, so meaning I would be using 0.75. But if I'm wrong, I would just resolve it with another shear lag factor. So from that itself, our PN, my PN is now equal to FU, and my FU is to be 448. So 448 megapascal times UAN, and my U is to be 0.75. So once again, this is to be this one right here, 0.75. So once again, I just guessed this. So if I am wrong, let's just resolve it later. So times AN, and our AN is also equal to 10 times 150. So 10 times 150. So solving for our PN right now, that is to be equal to, so 448 times 0.75 times 10 times 150. So that is equal to 504 kilonewtons. So kilonewtons. So I would just be dividing this by 1000 to convert it into kilonewtons. So divided by 1000, so 504. I forgot to solve for our PU and PA here respectively. So for our PU, that is to be phi PN, and our phi is equal to 0.9. 517.5 times 0.9. So this is to be 465.75. And for our PA, this is to be equal to PN over omega, and our omega is equal to 1.67. So solving for that, that is to be equal to 517.5 divided by 1.67. That is to be 309.88. So 309.88 kilonewtons. So for our tensile rupture stress, our phi PN in LRFD is equal to, oh, by the way, our phi is equal to 0.75. So from that, 504 times 0.75 is equal to 378. And for our Pn over omega, where omega is equal to 2.00. This is to be equal to, so 504 divided by 2, that is to be 252. So 252 kilonewtons. So I would just be erasing this part right here first for our comparison. So in these cases right here, once again, this is to be cross-sectional yielding and this is to be tensile rupture stress. And as you can see here, both of these values are less than this of these values right here. Thus, our governing factor for our PU and our PA would be 378 kilonewtons and 252 kilonewtons respectively. So PU kilonewtons. So we would be using both of these values right here for us to determine LW. Okay, so considering all of these values right here, we would now be solving for our LW. So we would be using this formula right here. From this range right here, which is 5 mm to 8.4 mm, as a designer, I think I would use 8 mm. So A is equal to 8 mm. But once again, it would be up to you on what nominal size you would choose, as long as it is in this range right here. So if we are to use LRFD, so for our LRFD, our PU is equal to phi RN or phi PN. And for our ASD, our PA is equal to PN over omega. So PN or RN over omega. And if we are to use these formulas right here to these formulas right here respectively, so this is to be equal to, so PU is equal to phi RN and our RN is equal to F and W times AWE. By the way, I would just be copying this to the next slide so that we would be having space. So there, and for our PU, that is to be 378 kilonewtons. So 378 times 10 raised to 3 newtons. And that is equal to phi, and our phi in welded connection is equal to 0.75. And our FNW, or the stress of the weld, is equal to, so going back to this table right here once again, it is 60% of FEXX, or the stress, the strength of our weld. So that is to be equal to, since we are to use E70 electrodes, that is equal to 60% of our E70 electrode. And our E70 electrode, so our FE70 is equal to 70 kips per square inch, since that is to be the label for of our electrode. So converting this to megapascal, it would give us an answer of 70 times 6.895, that is to be equal to 483. So 483. So this is to be 483. So this is to be for your FNW. And for our AWE, so that is to be equal to LW, so the length of the weld, times the throat. Throat is equal to 0.707 times A. And the A that I have chosen a while ago is to be 8 mm. So it would be up to you once again, as long as it is along this range right here. So times 8. Now solving for the unknown LW. So our LW right now is equal to, so look at the calculator to your left. So this is to be equal to 378 times 1000 divided by 0.75 times 0.6 times 483 times 0.707 times 8. By the way, we forgot something. Take note, guys, that we have our weld here and we also have our weld here. So we would be multiplying this by 2. So times 2. So times 2. Our answer right now is to be equal to 153.74 mm. And it is better for us to round this to round this up to 155 mm or 160 mm. So that is for LRFD. So what about for ASD? So similarly, our PA, which is 252,000, so 252 times 10 raised to 3 equals, so what would be our Rn once again? So our Rn once again is equal to FNW AWE divided by R omega, and our omega in shear in welds is to be equal to 2.00. And substituting everything that we know, so once again 252 times 10 raised to 3 is equal to what would be our FNW? That is to be 60% of 70 kips per square inch in megapascal, and that is to be 483. So 483. So once again, this whole right here is just your FNW. So there times the area of the weld, and the area of the weld is also equal to LW times 2 times our throat, which is I would just be putting it here, 0.707 times A, and the A once again that I have chosen is to be 8 mm. So there, we would be dividing all of this by 2. So now solving for the unknown LW, this is to be equal to, so 252 times 1000 times 2 divided by 0.6 times 483 times 2 times 0.707 times 8. So it is very similar with our answer here, which is 153.74 mm. So from that, we can conclude that the length of weld that we would be using is 155 mm or 160 mm. This would be chosen by the designer. So it would be up to you if you would be choosing 155 or 160 mm. If you can remember earlier, what we did here was to guess our value of U using these ranges right here. And as you can remember, I have guessed that my shear lag factor U is equal to 0.75, meaning I have guessed that the length of my weld would be between 225 and 150. So am I right? So the length of the weld that I have chosen is 155, so meaning it is correct. So meaning my shear lag factor is really 0.75. But if not, you would just be resolving it until you choose the right shear lag factor. And since once again, my guess is right that the length of my weld is in this range right here, so from that, we are now done with our design. So this is to be my conclusion. But what if we are to use 5 mm as our nominal size of the weld? Of course, your LW would come up. Would be longer. And if, for example, that it would be more than 225, so it would be up to you to resolve. So if it would be greater than 225 but less than 300 mm, you would be resolving it with a shear lag factor of 0.87. So that's it for this pre-recorded lecture. Thank you, everyone.